Hey there, science fans! Today we're diving into the exciting world of chemical bonds. Specifically, we're going to unlock the secrets of Fajan's rule. This rule helps us understand why some bonds are more ionic and others are more covalent. It's all about the interactions between atoms and their electrons. Chemical bonds are the glue that holds atoms together to form molecules. We often categorize them as either ionic or covalent. Ionic bonds involve a complete transfer of electrons from one atom to another. Covalent bonds involve the sharing of electrons between atoms. But here's the thing, most bonds aren't purely ionic or purely covalent. They fall somewhere in between on a spectrum. That's where Fajan's rule comes in handy. It helps us predict where on that spectrum a bond will fall. Pretty cool, right? So buckle up and get ready to explore the fascinating world of Fajan's rule. We'll learn about the factors that influence bond character and how this knowledge can help us understand the properties of different compounds. Let's go! Imagine two people playing tug-of-war. This simple game can help us understand the complex world of chemical bonds. If one person is much stronger, they'll easily pull the rope away from the other person. This represents a scenario where one participant has a clear advantage. That's like an ionic bond, where one atom, the stronger one, completely takes an electron from the other atom, the weaker one. The stronger atom exerts a force that the weaker atom cannot resist. Now imagine the two people are equally strong. Neither has a clear advantage over the other. They'll both pull on the rope and it will stay in the middle. This balance is crucial in understanding the nature of covalent bonds. That's like a covalent bond where the electrons are shared equally between the two atoms. Each atom exerts an equal pull on the shared electrons. But what if the two people aren't perfectly equal in strength? What happens when there's a slight imbalance? What if one is just slightly stronger? This slight difference can lead to interesting outcomes. In this case, the stronger person will pull the rope a bit closer to their side, but they won't completely take it away. This represents a bond with both ionic and covalent characteristics. This is where we start to see a blend of ionic and covalent character in the bond. The electrons are not completely transferred, nor are they equally shared. Fajan's rule tells us that the strength of an atom in a bond depends on two main factors, polarizability and polarizing power. These factors help us understand the nuances of chemical bonding. Polarizability refers to how easily an atom's electron cloud can be distorted. This distortion can affect the nature of the bond. Polarizing power refers to how strongly an atom can distort the electron cloud of another atom. This power can influence the bond's characteristics. We'll delve deeper into these concepts in the following sections. Understanding these principles is key to mastering chemical bonding. By understanding these factors, we can better predict the nature of a chemical bond and how it will behave. This knowledge is fundamental in the field of chemistry, so let's continue our exploration of Fajan's rule and see how it helps us unravel the mysteries of chemical bonding. The journey into the microscopic world of atoms and molecules is just beginning. Picture an atom as a fluffy cloud of electrons surrounding a tiny nucleus. This cloud isn't static, it's dynamic and constantly in motion, with electrons zipping around the nucleus in various orbitals. Now, imagine bringing a positively charged object close to this cloud. The positive charge exerts an attractive force on the negatively charged electrons. So what happens? The negatively charged electrons are attracted to the positive charge, causing the cloud to distort or become polarized. This distortion is a shift in the electron density towards the positive charge. The ease with which this electron cloud can be distorted is called its polarizability. Polarizability is a measure of how easily the electron cloud around an atom or molecule can be distorted by an external electric field. Think of it like squishing a marshmallow. Some marshmallows are easier to squish than others, right? The same concept applies to electron clouds. Similarly, some atoms have electron clouds that are more easily distorted than others. This difference in polarizability can affect how atoms interact with each other. So what makes an atom's electron cloud more polarizable? There are a few key factors to consider. 1. Size larger atoms have more electrons and a larger electron cloud, making them easier to distort. The larger the electron cloud, the more room there is for the electrons to move around and be influenced by external charges. It's like trying to hold a giant beach ball. It's much easier to squish compared to a small tennis ball. The larger surface area of the beach ball makes it more susceptible to pressure. 2. Shape atoms with more diffuse electron clouds, like those in larger orbitals, are more polarizable than those with more compact electron clouds. Diffuse electron clouds are spread out over a larger volume, making them easier to distort. Higher polarizability means that the electrons are held less tightly to the nucleus and are more easily influenced by external charges. This can lead to significant changes in the atom's behavior and interactions. This plays a crucial role in determining the ionic or covalent character of a bond, as we'll see in the next sections. The more polarizable an atom's electron cloud, the more likely it is to form covalent bonds. Understanding polarizability is key to unlocking the secrets of Fajan's rule. Fajan's rule helps predict whether a chemical bond will be more ionic or covalent based on the polarizability of the atoms involved. It helps us predict how easily an atom's electron cloud can be distorted by another atom, ultimately influencing the type of bond that forms. This understanding is fundamental in chemistry, as it allows scientists to predict and manipulate the properties of materials. Elements on the periodic table vary widely in their polarizability. For instance, noble gases have low polarizability due to their compact electron clouds, while alkali metals have high polarizability because of their larger, more diffuse electron clouds. By understanding these differences, chemists can design experiments and create new materials with desired properties. Polarizability is a key factor in fields ranging from material science to pharmaceuticals. In summary, the polarizability of an atom's electron cloud is a crucial concept in chemistry. It influences how atoms interact, the types of bonds they form, and the properties of the resulting compounds. As we continue to explore the fascinating world of chemistry, keep in mind the importance of polarizability. It's a fundamental concept that helps us understand and predict the behavior of atoms and molecules. Stay tuned for the next section, where we'll dive deeper into the implications of polarizability and how it shapes the world around us. We've talked about how easily an electron cloud can be distorted, a property known as polarizability. This concept is crucial in understanding how atoms interact with each other, especially in the formation of different types of bonds. Now let's delve deeper into the force that causes that distortion polarizing power. This force is what enables one atom to influence the electron cloud of another atom, leading to various chemical phenomena. Think back to our marshmallow analogy. Imagine the marshmallow as the electron cloud of an atom. The ease with which you can squish the marshmallow represents its polarizability. If polarizability is like the squishiness of the marshmallow, then polarizing power is akin to the strength of your hand squeezing it. The stronger your hand, the more you can distort the marshmallow, regardless of its initial squishiness. A stronger hand can cause more distortion, even in a less squishy marshmallow. Similarly, an atom with high polarizing power can significantly distort the electron cloud of another atom, even if that atom has low polarizability. In the atomic world, polarizing power refers to the ability of an atom to distort the electron cloud of another atom. This ability is influenced by several factors, including the size and charge of the atom. Atoms with high polarizing power are like those strong hands. They can significantly distort the electron clouds of other atoms, even if those atoms have low polarizability. This distortion can lead to changes in the chemical properties and reactivity of the atoms involved. So what makes an atom have high polarizing power? There are two main factors to consider: the size of the atom and its charge. First, let's talk about size. Smaller atoms have a higher concentration of positive charge in their nucleus. This concentrated positive charge exerts a stronger pull on the electrons of nearby atoms, making it easier to distort their electron clouds. This concentrated positive charge exerts a stronger pull on the electrons of nearby atoms. The smaller the atom, the more intense this pull, leading to greater distortion of the electron clouds of neighboring atoms. The second factor is charge. Atoms with a higher positive charge have a stronger attraction for electrons, making them better at distorting electron clouds. This is because the increased positive charge enhances the atom's ability to attract and influence the electrons of other atoms. High polarizing power and high polarizability often go hand in hand in promoting a more covalent character in a bond. When an atom with high polarizing power interacts with an atom with high polarizability, the resulting bond tends to have more covalent character due to the significant distortion of the electron clouds. Think of it like this. A strong hand, high polarizing power, can easily squish a soft marshmallow, high polarizability. This analogy helps us understand how the interplay between these two properties can influence the nature of chemical bonds. In the next section, we'll explore how the interplay between polarizability and polarizing power influences the ionic character of a bond. Understanding this relationship is key to predicting the behavior of different substances and their interactions in various chemical reactions.